Hello and welcome back to, I believe, week number 8 now. And we are in lecture 15, I think, of Math 211. And we are going to continue our discussion on variability. How fun is that? Any questions on anything we've done so far? Okay, if not, let's share the screen and let's get started. Hold on, let me unshare for just a second so I can close these down. Okay, here we go. Okay, so last time we talked about the mean absolute deviation as a measure of variability. We know how to find the mean, which is the balance point. And we did that last time. Oops. We did that last time and we saw that each of these had a mean of 6. So the mean of all of these is 6. But when we look at the spread of the data, we see that while they all have a mean of 6, the first one is kind of all over the place. The second one has some on the far left and some on the right. The third one has almost all in the middle with a couple on the edges. And the fourth one has a bunch in the middle and then a little here and then a little more there. So they all have the same mean, but their spreads are all different. In fact, same mean and same range. Remember, range is max minus min. So not only do they all have the same mean, they all have the same range. So range is not really the best measure of spread because some of these 4 are more spread out than others, but yet the range gives the same value for everything. So we invented this thing called the MAD, the mean absolute deviation. Mean absolute deviation, where what you do is you see how far each thing is from the mean. So since we calculated the mean to be 6, how far is 2 from 6? It's 4 away. How far is 3 from 6? It's 3 away, and this and so on. And we add them all together to get the total. We did that for troop C as well. Anyone recall what the total was for troop C? I think we did it last time.
It was 8, I think.
Was it 8? Which told us that troop C had a lot less variation than troop A because its number was so much smaller. And then we had the following question. I don't know if we got this far or not, or this is where we ended. But I said, okay, what if we have a new troop, a 5th troop, where it had 40 girls, 20 of whom sold 5 boxes and 20 of whom sold 7 boxes. And we have its distribution, which is right here. This is the shape of its distribution. We see it has the same mean of 6, but it's not as spread out as troop A, which is all over the place. Troop E is not all on 6, true, but everything is pretty close to 6. Lots of things really close to 6. Nothing far away. But if we calculate the MAD for group E, what do we get? What's the MAD for group E? How far is each data point from the mean? How far is each data point from the mean? How much?
1.
1. And how many data points are there?
40.
40. So if I sum it all up, I get 40. And that's a lot more than what I got for group A. Let's calculate what it is for group A. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So group A had a MAD of 20. Group E has a MAD of 40, which would indicate, if the MAD is really a good measure, it would indicate that group A is a lot less spread out than group E, because group E's number is so much bigger. And yet we have this intuitive feeling that group E should have the smaller variance because all of its data points are really close to 6. Whereas in group A, a lot of them are far away. So does it seem sensible? Does it seem sensible to say that the sales from troop E are more variable than troop A? We get a bigger number, 40 versus 20, but intuitively, do we feel that group E has more variance? And the answer is no, we don't feel that way. Everything in group E is close. Group A is all spread out. So give me a reason why you feel that group E's MAD should be so high compared to group A's if group E has a smaller variance. What would be a reason for that?
It's because of the dot points, right?
I'm sorry?
Troop B has more dot points,
Troop E has more points, more data.
more data.
By more data. Every point is a piece of data, right? Troop E has 40 data points versus versus A, which only had what, 10? 1, 2, 3, 4, 5, 9. It only had 9. So the issue is that when you have lots and lots of data points, each one contributes a little bit, but eventually it's going to add up to a bigger number. And that's why the MAD is so much bigger for E than it is for A. It's not because it has more variance. It's because you have so many data points, it's going to add up to a bigger number. So how do we get around this issue? What we do is we don't just add them up. We then divide by how many data points we have. So in the case of E, for example, we got 40 as a sum, but then we divide by 40. So what do we get for E? What's the overall true mean absolute deviation for E? If when you add them all up, you get 40, but then you divide by how many data points you have, what do we end up with? This is the part where you answer.
Just the one, right?
Just the 1. Whereas for A, what do we end up with? What was the sum again for A?
20.
20. How many data points were there?
No.
Sorry?
It was 20 divided by 9.
20 divided by 9, which is like 2 points, 2 bar, 2.22 or so.
Yeah.
So we see that when you include how many data points you have, it's a much better measure because then it takes into account that some groups are bigger than others. And now we see that E has a much smaller variability than A, which is expected. And we return to the notion that the mean absolute deviation ain't half bad. It was looking good. We did an example where we're like, wait a second, this makes no sense. This can't be horrible. And then we said, no, just fix it a little bit, divide by n, and everything's right again in the world. So this formula here is the ultimate final formula for the mean absolute deviation. You find how far each data point is from the mean. You add them all together, making them all positive, because I don't care if it's to the left or to the right. I just want to know how far. And then you divide by how many data points you have, and that gives you the mean absolute deviation. Does that make sense as a formula? Yes, no, maybe so. Anyone?
Yep, makes sense.
Makes
Okay.
sense.
Now, the reason why we use absolute values, of course, is because if we didn't, then the positives and the negatives would all cancel and you get 0. That doesn't really mean much. If every distribution will always give you 0, it's kind of a silly measure to use. Hey, what do we have here? 0. How about there? 0. Oh, okay, that's more variable. If everything is 0, you get nonsense. So how do we make things positive? We take the absolute value. -4, make it +4. -2, make it +2. 7, keep it. If it's positive, keep it positive. If it's negative, make it positive. Now, you can't get negatives anymore, so you get a useful measure. What's something else we could have done besides absolute valuing to make things positive besides that? What could I have done besides taking absolute values to make things positive? What's something else I could have done? Besides making things positive. Besides absolute valuing to make things positive. I could have squared everything. Do you agree that squaring things makes them positive?
Yep.
So I could have squared things as well. If I would have squared everything, it also would have made things positive. And that's what the standard deviation does. The standard deviation squares them instead. Now, of course, if I square them, then I'm going to have the wrong units. If everything was like feet, 5 feet, 3 feet, 2 feet, 7 feet, and so on, and then I square everything, I no longer have feet. What do I have instead?
Square feet.
Square feet. So how do I get rid of having square feet? At the end, I
Use the
take the
square
square root.
Yeah.
Right? You square, you add them all together, and then you take the square root, correct? Of course, let's not forget, like the mean absolute deviation, you also want to divide by how many data points you have. So we're going to divide by how many data points. Oh, wait a second. We don't divide by how many data points. We divide by one fewer than the number of data points. Does anyone know why it's one fewer than the number of data points? Anyone want to take a guess as to why it's one fewer than the number of data points? Anyone want to just say something so I know you're here and you're listening?
Yeah, I have no idea, but I'm sure when you tell us, it'll hit me. So
You know what? It might not. It's actually not. It's not the
same thing.
it's not the simplest thing, actually. Sometimes it's like, I don't know, and then I say, like, oh yeah, that makes sense. This one might not actually. So let's remember the overall purpose to statistics in general. What we're doing is we're taking samples and we're using information from samples to get a bead on true values. Like, I don't know the true height of every American. I'll take a sample of 1,000 people. I'll get the average of my sample, and I'll use that and say, my best guess for everyone is what I got from my sample. Does that make sense?
Yeah.
Yes, using samples to measure things, they're our best guess. Now, if I'm curious about the average height of every American, I can do one of two things. I can do lots of things, but consider the two possibilities. I take my sample of 1,000 people and I use the average of my sample, or I take the sample of 1,000 people and I use the tallest person in my sample. Which of those is a better guess for the actual true average of everyone? The average of my sample or the tallest of my sample?
the average.
The average. What's wrong with the tallest of my sample? It's probably not going to be anywhere near the true value, correct?
Yep.
So when we estimate, there's our estimators fall into two categories, what are called unbiased estimators and biased estimators. An unbiased estimator is one where I expect the sample value to give us a good approximation of the true value. The actual average of my sample is unbiased because I expect, if it's a large enough sample, that it's going to be a pretty good approximation. But if I take the tallest of my sample chances are it's not going to be a good guess for the true value that I'm looking for. We call it a biased estimator. If you divide by n, which is what is the intuitive thing to do, it can be shown mathematically that you end up with a biased estimator for the true standard deviation. Whereas if you divide by n minus 1, mathematically it turns out to be an unbiased estimator. So it's not necessarily something that you would have guessed. It's just the way the math works out. Dividing by n minus 1 just gives us an approximation that is more accurate than dividing by n. Now, if you take a number like 10 and divide it by 1, you get 10. Divided by 2, you get 5. That's a pretty big difference, correct?
Yep.
But if you take 10 and divide it by 1,000, and then divide it by 1,001, the difference is a much more negligible. 10 over 1,000 divided by 10 over 1,001 is a difference between 0.01 and 0.099901. They are extremely close to each other. So when the sample size gets larger, the difference is more and more negligible. But nevertheless, n minus 1 is technically a slightly better value than n. That's essentially what it comes down to.
Okay. So if you want us to find the standard deviation of everything, though, we should just use this formula.
This is the formula for the standard deviation of a sample.
Okay.
If I magically gave you the entire population, then you would divide by n. But every sample we divide by n minus 1.
Got it.
Now, on the surface, it looks like this is more complicated than the mean absolute deviation, and it is more complicated. It's just has much better mathematical properties to the point that we just never use the mean absolute deviation in practice. We always use the standard deviation, but on tests, it's a lot easier to calculate the mean absolute deviation than it is the standard deviation. So on tests, I tend to give more examples of the MAD than I do for the SD, just because it's easier to do by hand. Okay, but in general, the SD is better. So let's go ahead at least once and calculate the standard deviation for troop A. If you recall, for troop A, the boxes were 2, 3, 4, 5, 6, 7, 8, 9, and 10. What was the mean of these guys? What's the mean of 2, 3, 4, 5, 6, 7, 8, 9, and 10?
Wouldn't it be 20?
I don't think it's 20. The mean, not the mean absolute deviation, the mean. How do I find the
Oh.
mean?
So for 2 it'll be 4.
I'm sorry?
For the box 2, the first one is 4 for the mean.
No. Just what's the mean for the whole, for all of these? It's one mean for the whole thing. Yeah, it's just 6. Right? Didn't we say it was 6 for all of them?
Yeah.
Yeah, where they all met in 6.
I mean, how do you find, yes, they all, exactly. But I'm saying mathematically, how do you find the mean of a sample?
You just add them up and divide by however many there are.
Add them up and divide by how many you have, right?
Mhm.
So 2 plus 3 is 5, 9, 14, 20, 27, 35, 44, 54. 54 divided by 9 is 6. So the mean is 6.
It took me much longer to add those up.
Sorry. I feel for you, I do. Now, what's the first deviation? What is 2 minus 6?
-4.
-4. And what is its squared value?
16.
16. What is 3 minus 6?
-3.
Its squared value?
9.
Next,
-2,
its squared value.
4,
Next,
-1,
squared.
1,
Next,
0, 1,
whoa there, buddy.
0,
0. Next,
1, 1, 2, 4, 3, 9, 4, 16.
okay, excellent. And what's the total if I add these guys? Taking too long.
It's a 60.
60.
60. 16 and 4 is 10. 9 and 1 is 10. So that's 20. Sorry. 16 and 1 is 20 and 9. Try that again. 16 and 4 is 20. 9 and 1 is 10 for a total of 30. And then same numbers here. So a total of 60. So when I get to the standard deviation, I have the square root of 60, which is the sum of the squares, divided by what?
So it's going to be 6 minus 1?
Why 6 minus 1? What's n referring to?
10.
Not 10.
9.
So if n is 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, right? 9, n is 9. Then what is the denominator going to be?
8.
8. And what is the square root of 60 over 8?
$2.74. If you round it.
Yeah, approximately 2.74. So the standard deviation is about 2.74. Yes?
Yeah.
Okay. What did taking the square root accomplish? What was the point of that?
Doesn't it ensure that we have the absolute value?
Well, what do you mean by that? We don't have absolute value here, do we? Someone chatted, they said, bring back values to original. Be more specific. What do you mean bring back values to original?
So when you square the number, it changes it from a negative to a positive and keeps a positive, and then rooting it sends it back to the value that it would have been if we absolutely
Really?
valued it.
You sure about that?
Now I'm not.
Are you telling me that if you take the number like -4 and you square it, what do you get?
You'd get 16.
And if I square root that, what do I get?
You're going to get 4.
Not -4. I never go back.
Yeah, well, it's not going to be the original value. It's going to be the absolute version value.
Okay,
I don't know
well-
how to describe it.
No, it's fine. The absolute version value. In fact, a lot of people think that the square root of x squared is equal to x, but it's not. The square root of x squared is not equal to x. Look here, the square root of -4 squared is not -4. The square root of x squared is the absolute value of x. It's the positive version. But if the whole reason is to get positives, why square root it? I had positives when I squared them. The question is, why am I square rooting? So someone said bring back values to original, but we don't. They stay. They're different. If it was negative, it's not going to become negative. And Angelica, you say to have positives, but we have positives. Right? I don't need a square root to get positives. I have positives by squaring. So again, the question is, what did taking the square root accomplish? Someone said for fun. Well, I don't know how you have fun, but the rest of us do not have fun by square rooting. All right, maybe cube rooting. Now we're talking. But square rooting, no. Square rooting is not fun. Well, okay, I kind of enjoyed it a little bit. Now, I already said the answer. I said it earlier. It's to bring the units back. Because remember, if I have measurements in feet and I square each measurement, what are my units now?
Squared, like centimeter squared, feet squared.
Feet squared, centimeter squared, something squared, correct?
Correct.
So if I square root feet squared, what do I have now? If I square root feet squared, what do I have now?
You have feet.
I'm back to feet. So square rooting brings us back unit wise to the original. That's why we do it. And then yn minus one. So you can just read this quickly. Although there's one thing about this that I don't like. Can anyone guess which part of this entire paragraph I hate? Take a guess. Which part of this? Which words do I hate so much?
Technical and frankly not very important. Are those
Nah.
the words?
Well, I don't care about the somewhat technical part, but frankly, not very important. Frankly, not very important. What? So whoever wrote these notes should be shot. Not literally, but maybe it's like no longer politically correct to say a joke like that, but certainly this is not good. It is very important. It just might not be important to you guys. But she is right. She is right, or he, that it is somewhat technical. So I gave you the reason earlier about it being unbiased or biased. You don't have to know that. I just kind of felt important, so I said it. So let's do this example. Jade has a mean test score of 69 and Jason has a mean test score of 76. First, how do I confirm that those are correct and a mistake was not made?
You can add them up and divide by the number.
Yeah, so let's do that just quickly. 20 plus 65 plus 80 plus 85 plus 95 divided by 5 and 73 plus 74 plus 75 plus 78 plus 80 divided by 5. Okay, they both work. So just looking, which student had test scores that vary more from their mean?
Jade.
Jade. Let's calculate the standard deviation for each student and see if that is backed up. Let's do the first one. Let's make a table. First, we'll have our data points. 20, 65, 80, 85, and 95. For the first column, write your deviations, 5 deviations. Go ahead, please, and write your deviations. Okay, what's the deviation for 20?
That's 7.
I don't think it's 7. Where did 7 come from?
Oh, I did 20 minus 69, which is negative 49.
Negative 49. Sabina, you wrote 49, but it's Angelica's right. It's negative 49. It's data point.
Oh, you're talking about the,
Yeah, data point minus the mean. And what's the next one?
-4.
Negative 4. And good. What's the next one?
11.
11. And the next one?
16,
16. And the next one?
26.
26. Now, what are the deviation squareds? I was gonna write SD for square root of the deviations, but SD is kind of means something else. So what are the squares of the deviations? What's the first one?
That's-
2,401.
Good, 2,401, Sabina had a 2 in the chat. Okay, what's the next one?
16.
16, next one.
121.
Good, next one.
256.
256, and next one.
676.
Great. And now, what do we do with these 5 numbers?
Add them.
Add them. And what do we get when we do? What is the sum of those 5 squares?
Professor,
3,361.
How much is it?
3,361.
About 470.
I got 3470 as well.
Professor, what's the first number?
2401.
2401. Oh, okay. Sorry, I couldn't read it.
You're saying I have bad handwriting?
No, no.
You know, I won best penmanship in 2nd grade. Still my finest achievement in my life. All right, so what do I do with 3470? Divided by 4, excellent. Divided by 4 and minus 1, 5 data points. So divide by 4. And then what do I do with that number?
Square rooted.
Square root it. So what do I get approximately? What do I get approximately?
I got 29.45.
29.45, we'll round to 29.5, 366. Okay, now let's do the same thing for Jason. We have our 5 data points, 73, 74, 75, 78, and 80. Just by looking at it, I can tell these numbers are so closely, more closely packed than they were before. So I would like you, without stopping for me every step of the way, I'll do it here. I would like you to go all the way and calculate the standard deviation. Got it. First person who gets it, put it in chat.
Professor, I have a question.
Yeah,
Earlier, why did we divide by 4?
how many data points are there?
5?
And what do we divide by in the formula? If you look-
Oh, got it. We-
Right, okay.
Professor, do I tell you the one on the next line for the answers for the D?
Yeah, but Tyler beat you to it.
Oh, never mind.
You have the same thing?
I probably did, yeah. I'll check right now.
2.92?
Yeah.
2.92.
Excellent. And notice, by the way, if you add up the deviations, you always get 0. All right, so obviously here, we get a much smaller standard deviation for Jason compared to Jade. So the standard deviation is, on the surface at least, looks like a pretty good measure of variation.
Wait, can you
Uh,
go back for one second, or is it erased already?
Oh, let's see, undo, oh, there it is.
Okay, 2.92, and what did you do? You did 34 divided by
34 divided by how much?
By 4 and then
by
squared.
4. Okay. Oh, and then squared it. Okay, perfect. Thank you.
Yeah, then squared. Sorry, someone else have a question? Yes, no, okay. Okay, so now just looking at these three, A, B, and C. Each one has roughly the same mean and range. The mean is roughly right in the middle. The range is 6 minus 1 is 5. It means about 3.5, give or take. Which of those three has the largest standard deviation? Which one has the smallest? And give me a Y as well. So don't just say the answer, because it's basically a
So wouldn't A have the largest standard deviation?
A, why A?
Because the numbers are so like different from one another.
They are different, but I'm looking for something more than that, because I can make a distribution where some numbers are different than others, but not have it be the largest. There's one thing in specific that I want you to focus your attention on, which may be what you meant, but it's not what you said. What does standard deviation measure? It measures how far on average data points are from the mean. Which deviation has most of its data points far away from the mean? Or at least a significant portion of them. Which of those three has lots and lots of data points far from the mean?
A.
A. The majority of the data points are on the far left and the far right, and in relatively fewer near the mean itself. Which of them has most of its data points close to the mean and very few that are far away?
See,
C? No, B does. If you look at B, the majority of them are between 3 and 4, some 4, 2, and 5, and very few 1 and 6. The majority of them are really close to the mean, correct? For C, the same numbers by the mean as is far from the mean. So the C is kind of like a middle ground between A and B. Does that make sense?
Yeah.
Everyone?
Yes.
Okay.
Yeah, makes sense.
So A has the largest, B is the smallest, C is somewhere right in between. So let's just go over that one last time. 3 ways of measuring variability. We have the IQR, the MAD, and the SD. When do I use which one? The IQR is used if I'm going to be using the median. IQR always goes with the median. When do I use the median? If there's a lot of skewness, if it's strongly skewed, or there are outliers. In that case, the mean is very easily changed, but the median resists very well. So I want to use the median if it's strongly skewed or there are outliers. When do I use the standard deviation? If it's not strongly skewed and there are not outliers. The 2 reasons why I would use the median, if they're not there, use the mean. And what goes with the mean? The standard deviation. When do I use the MAD? Never. It's just a measure to help lead into the standard deviation and on tests and stuff where the math is a little bit easier. But we don't use the MAD out there in the world. We use the SD and we use the mean. Okay? Now, if the MAD is 0, if the mean absolute deviation of a sample of data is 0, what can you tell me? What is the one thing you can conclude if the MAD is equal to 0? What can you conclude if the MAD is equal to 0? Remember what the MAD is. The MAD is the sum of the deviations of the absolute value of the deviations divided by n. If a sum of positive numbers, or at least non-negative numbers, is 0, what can you tell me about each one of those numbers?
You have no deviations.
Well, deviations are when you compare things to the mean. I'm just asking about the numbers themselves.
Oh, okay.
If the sum of a bunch of positive numbers is 0, or not always, if the sum of a bunch of non-negative numbers is 0, what can you say about those numbers?
Well, they're equal.
More than that. Give me an example of 3 numbers that add to 0, but you can't use negatives. Go.
Aren't they all 0?
They all have to be 0. Every deviation must be 0. There's no other way for the MAD to be 0. Now, if each deviation is 0, what does that mean? What does it mean for a deviation to be 0?
All your data points are like on the mean,
And therefore, all your data points are
equal.
equal. Excellent. If the MAD is 0, all data is the same. What if the SD is 0? What could you conclude then? Remember what the SD is. It's a sum of squares over n minus 1. Or the square root of the sum of the squares over n minus 1. If that's equal to 0, then what can you tell me about the squares themselves?
Wouldn't they also be equal to 0?
They're all equal to 0, which tells me. What's the conclusion?
Then there's like not really any deviation between the numbers.
And therefore, what can you conclude? What's the final statement that you're going to make about the data itself?
They're all the same.
They're all the same. If the SD is 0, all the data is the same. What if the IQR is 0? What if the IQR is 0?
Then the Q1 and Q3 would be the same.
Yes, yes. And if Q1 and Q3 are the same, what does it tell you about the data? Wow, you got it. You're so close. If Q1 and Q3 is the same, what do you know about the data? What is Q1? What is Q1 of a data set?
The smallest, no. The smallest.
Let's say again, what?
The smallest number?
No, min is the smallest number. Q1's not the smallest number.
Oh, yeah.
What's Q1? What's another name for Q1?
The 25th percentile?
The 25th percentile. And what does the 25th percentile mean?
The median of the first quarter.
True,
Numbers?
but that's true. But what is the 25th percentile by itself? If I said, what's the 80th percentile, the 40th percentile, the 26th percentile, the 25th percentile, the 100th percentile, what do percentiles mean? What's a 25th percentile?
You are above or at 25%.
Okay, and what's Q3?
You are at or above 75%.
So if Q1 and Q3 are the same, what does it tell you about the data?
The same.
What's the same?
All of it?
Not all of it. No, that's not what the IQR says. Not all of it. Doesn't say the min and the max are also equal to that. It just says Q1 and Q3 are equal to that.
Means that 75% of the data at least is the same.
Not exactly, but the middle 50% is the same.
Okay.
The middle 50% is the same. Was that what you were saying? I heard a voice that I think said something like that as I was saying it.
Yeah, as you were saying, I was saying the middle 50% of your data will be the variability.
Yes, because not the variability, but it will be
Oh
the
yeah,
same.
yeah, will be the same.
Q1 to
25
Q3.
and 75. Yeah.
Right. The middle 50% is Q1 to Q3. If Q1 and Q3 are equal, all of that 50% collapses to one data point. But I can still have less than that on the left and more than that on the right. I don't know about that. But at least the middle 50% is the same. Correct? Make sense?
Professor, in the previous page,
Yeah.
did we do the what is the mean and what is the range?
Well, the mean is about 3.5.
Okay.
It's like, it's pretty symmetric about 3.5. And the
Mhm.
range is 5, 6 minus 1.
6 minus, because you take the biggest and
Minus
the,
biggest minus the smallest.
okay.
So I don't care how many big ones I have and how many small ones I have. It's just biggest minus smallest. Make sense?
Yes.
I hope so. All right. So we finished chapter 13. Which is great. So I'm going to stop sharing for a minute. When I go to files, Let's see what 14 is. 14 is. Come on, 14, open up. Oh, 14 is important. Oh, yeah, 14 is fun. Okay. 14, muy importante, very important. Okay, so. Yeah, so we finished 13 today. You have a quiz due on Thursday. We'll have another quiz over the weekends. And we'll decide on Thursday what chapter it should be on. How's that?
Sounds good.
That sounds good. Okay. I don't want to start 14 now. For two reasons. We're not going to get very far into it. And I got a big headache. So we're going to stop a few minutes early today. And we'll start 14 next time. So are there any questions?
No, thank you.
No problem. I will see you all on Thursday.